Hi, this is the second lecture on mining geostatistics. In this lecture, we'll see the recovery functions concept and the support effect on these recovery functions. Okay, after we create the grades estimate the grades in a regular grid of points inside each ore body, all inside each ore type, as you could see in the last lecture, we can present the results as maps, 3D views, histogram of grades, etc. This is normally called geological resources, where there is no technological or economical constraint of the existing resources. Another different concept are reserves. That is to say, some resources that can be considered reserves when they can be mined. We can say a reserve is a resource that is economically, technologically, and environmentally exploitable. We are going to see in this lecture how to quantify and parameterize the reserves through tonnage, quantity of metal, and average grades through a concept of recovery functions. But first, let us see the different concept of cutoff grade. Cutoff grade is the metal grade above which all reserves are to be mined and under which are to be rejected as waste, are not reserves. So, recovery functions can be considered the reserves above a given cutoff grade. Tonnage, for example, the tonnage above a cutoff grade, quantity of metal and average grades above a cutoff grades, etc. Okay. So let us see a simple example. Suppose a panel with 20 blocks with copper grades. Let me show you. Those are the blocks, left-hand side column, and those are the grades, copper grades of those 20 blocks. Okay. Now we can compute the number of blocks above the grades. So we can just rank ordering by increasing order the grades, and you can see that above, for example, and you do the same for the number of blocks, and you can see above the minimum grade you have 20 blocks, above 0.4% we have 19 blocks, etc. For example, there are 15 blocks above 1% of copper. There are 10 blocks above 2% of copper. Okay, so if we assume each block with a given tonnage, for example, one block, 1 ton, we can just represent represent the same table here, but related with the tonnage above a given grade in terms of relative tonnage. For example, above 0.3% of grades, we have 100% of all tonnage, which is, for example, 20 tons. Above 0.4, we have 0.95, 0.85, etc. There are 75% of total tonnage above 1% of copper. We can also represent it in a diagram, express the tonnage recovery function, because this is what we call the tonnage recovery function, in a graph. We can see that is a decreasing function. We have in x-axis we have the copper, and this is the tonnage, relative tonnage. So let's let's define the tonnage, the recovery function tonnage above a cutoff grade. T above ZC, the cutoff grade, is calculated, can be calculated the set of n available values of grades here. So we create the indicator function that takes the value 1 if the grade is above the cutoff and 0 otherwise, and the tonnage above a given cutoff grade is no else than the average of those indicator values of zeros and ones here. Okay, simple. Quantity of metal. The quantity of metal, for example, in this case we have each block is 1 ton, so the total tonnage is 20 tons. The average grade is 2.11%, the average grade of those of copper. So the total quantity of metal, I mean the copper contained in those 20 blocks, is about 0.4 tons, okay, or 422 kilos, okay. That's the concept of quantity of metal. Okay, so we can represent the same way we did with the tonnage, the quantity of metal the same way. So above the minimum value of grade, we have 0.42 tons of copper. For example, here above 0.7% we have 0.41, and so on and so on. So there are 0.08 tons of metal above 4% of copper. As you can imagine, this is also a decreasing function. Here it is. Okay, so we can represent also the quantity of metal in relative terms. The total quantity of metal of the panel of 20 blocks is 0.42 tons, so this is 100%, 0.9%, 99%, and so on. You can represent it in relative terms, a decreasing function as well. Now, by definition, we can define the quantity of metal exactly by the product of the indicator function that takes value 1 if the grade, one given grade, is above ZC, the cutoff grade, 0 otherwise. So the product between this indicator and the grade itself is the quantity of metal. So the average of the average of all blocks here gives me the quantity of metal above given cutoff grade. So the last recovery function that I have to show you is the mean grade. Mean grade, so, is the ratio between quantity of metal and tonnage by definition, because quantity of metal is the product of tonnage and the grade. So if we do this ratio, you obtain the mean grade recovery function that can be represented this way. Okay, but there's a difference of this last recovery function, median grade, because it's an increase function. It means that the cutoff grade decreases when the cutoff grade ZC decreases. It is to be mined more tonnage, more quantity of metal, but with a lower quality, which is the mean grade. When the cutoff increases, is the opposite. The quality, mean grade, increases, but the quantity of metal and tonnage decreases. That's the way it works with recovery functions. That those are basically tools that help us to plan and to decide about the available reserves of a given body, of a given part of our body, etc. Okay? So let's see the support effect, which is the support effect is the reduction in spread, in symmetrization of a block histogram. Let's say, for example, have a look to this. Compare the point support grades. They have larger variance. If we start put together in blocks those point grades, we'll get the block grade histogram with this, which is with a lower variance. Okay. Another we'll return to this point in the next lecture, but just to tell you that estimated creaked blocks increase the support effect, and the bias estimate of extreme values of reserves. And the point is extremely important, and you are going to see afterwards that is that the decision whether a block is to be mined or not is made on block estimated grades. This is the only one that you have. You create the block, you have the estimate, and we decide if it is ore or not. But the ore processing plant receives as input the real block grades. And this is the difference between estimated block grades, lower variance, and real values block grades. We are talking about same support, but one is estimated and the other is the real values. So that's a big difference that you see. But now we'll see, I want to show you the support effect and spatial continuity of mineralization. Spatial continuity of local heterogeneity, local variability of the grades in a given mineralization. For example, I try to represent here two different realities with the same histogram, with the same mean, same statistics, but different spatial continuity. In the left-hand side here, we have high continuous bodies, high continuous spatial patterns of high grades, low grades, and so on. And in the right-hand side, we have a more unstructured spatial pattern. I mean, with this salt and pepper. And if you remember your classes on introductory geostatistics, you will remember what the nugget effect is. Okay. Now, now we have here two scenarios. The scenario one is represented by high spatial continuous and anisotropic structure. Here is the image. This is the histogram and the variogram. And we have scenario two, which is more chaotic, more unstructured spatial pattern of the same grade, same histogram. Same mean, same variance, but different spatial patterns with almost poor nugget effect. Okay, so now let's do an exercise. Just take the real grades of point grades and just and we calculate blocks of 10 by 10 points, and this is what results from this image. Okay. And we can compare the statistics. The mean of the point of point images, point image, sorry, is 11.9, and the block is the same. We are calculating in the same area, but look at the variance. The variance of point support is 29.2, but the variance of block is 22.1. Decreases. This is the support effect. Okay, it's normal. Now let's do the same exercise, but now with the scenario, unstructured scenario. Okay, we just averaging in each block of 10 by 10. As you can imagine, in this situation, the probability to mix in the same blocks high and low values is higher than in the previous scenario. Okay, so let's see the statistics. Statistical points we have already seen: 11.9, variance 30.5, same. But in the blocks, the average is the same because we are talking about the same region. But look at the variance, decreases from 30.5 to 4.3. Okay, decreased a lot. Okay. So this is a summary, and you can see the difference of those two block support maps. Okay, with the statistics. Now let's see the support effect. This is the same support effect, but on tonnage and quantity of metal of scenario 1, which means with negative effect is 0. The pretty much continuous pattern. So as you can see, this is the point, is the blue dots, and the block is the red blocks, and almost no, you almost don't see any difference between the tonnage, the quantity of metal, and so on. Okay, can you see? Now let's see in the other situation. The more chaotic, the more unstructured, and you can see that the effect on those tonnage and quantity of metal are quite strong. So you can see this is the point, but now the block there's a huge difference between the point and the block in the tonnage recovery function, and as well in the quantity of metal. So support effect is considered as a reduction in spread and symmetrization of block histogram. The effect of support is greater for spatial uncorrelated mineralization, is greater when there are higher local variability of grades. Okay, as the mineralization is more spatial continuous, the support effect decreases a lot. And sometimes, in some situation, you cannot differentiate between point and block. So this is the end of this lecture, and in the next that's all I had to show you. But in the next lecture of mining geostatistics, we'll see the information effect and the recovery functions. Okay, thank you.